Let's start with a wild idea. What if an AI could be tricked? Not with a riddle, but tricked into seeing a reality that's completely different from ours, something that just isn't there. Okay, let's dive into this because we are about to explore the absolutely fascinating and yet slightly unnerving world of adversarial machine learning. Now, before we get started, just a quick heads up. This is part 5 of a 10-part series. It's an overview based on a really comprehensive report from Virtualization Options LLC, which goes way deeper into all of this stuff. All right, let's get into it. So, here's our game plan. First, we'll look at what's called the invisible attack. Then, we'll peel back the curtain on hacking the model's mind. After that, we'll talk about detecting digital deception. And finally, we'll wrap up with how we can start building a resilient AI. All right, so let's start with the big mystery here, the invisible attack. This is where AI systems get fooled by changes to images or data that, to you and me, are completely invisible. This is the classic example, and it is a real mind-bender. On the left, we all see a panda, right? No question. But get this, an attacker adds a layer of carefully calculated invisible noise to that image. To us, it looks exactly the same. But to the AI, it sees a gibbon, and it's 93% sure about it. We see a panda, it sees a totally different animal. That right there is the heart of the problem. And this isn't just some weird party trick. Think about the stakes in the real world. The source material brings up a chilling example. A self-driving car could look at a stop sign that just has a few tiny, strategically placed stickers on it and just not see it as a stop sign at all. The consequences there? Well, they could be devastating. So how on earth is this digital magic trick even possible? Let's pull back the curtain and look at the actual mechanics behind these attacks. How do they actually hack the model's mind? The secret ingredient here is something called adversarial perturbations. I know, it sounds super technical, but the idea is actually pretty simple. Attackers create this layer of what you can think of as invisible noise and add it to an input like our panda picture. We can't see it, but this noise is specifically designed to exploit the AI's internal math and push it towards the wrong answer. But that brings up a really big question, doesn't it? How can an attacker create this perfect invisible noise if they can't even see the inner workings of the AI they're trying to fool? You'd think they need the blueprints to the system, right? Well, it turns out attackers have some pretty clever tricks. We've talked about the digital noise, or the perturbations. Then you have physical attacks, like those stickers on a stop sign. There's also something called black box evasion, where an attacker just throws a bunch of different inputs at the AI and learns its weaknesses by watching how it responds. And maybe the wildest one is transferability. It means an attack that works on one AI model will often work on other similar models, so attackers can practice on a dummy model before going after the real thing. Okay, so we understand the threat. Now let's flip the script. How do we fight back? How do we find the invisible fingerprints these attacks leave behind and actually detect this digital deception? Now, there's no single silver bullet here. It's all about a multi-layered defense. You start with statistical analysis to find anything weird. You monitor the AI's confidence levels. You can use multiple AIs to vote on an answer. You can try to clean up the inputs beforehand, and you can run behavioral checks. Let's look a little closer at that first step. Think of statistical analysis like a forgery expert looking at a signature. That expert knows what a real signature looks like, down to the tiniest details, so they're looking for anything that's just a little bit off. These detectors do the same thing, but for data, they scan for statistical oddities that just scream, "This isn't normal." And here we have a really powerful technique, ensemble validation. It's basically like getting a second opinion from a few different doctors. You show the same image to several different AI models. If two of them say panda, but a third one shouts gibbon, that disagreement is a huge red flag that something is wrong. Catching an attack is great, but building an AI that can resist them in the first place, that's the real goal. So for our final section, let's talk about how we can move from just detecting to truly defending. The strategy really breaks down into two parts. On one side, you've got remediation. That's the fix for what to do after an attack happens. But on the other, more important side, you've got prevention. That's the shield you build to make the model stronger from day one. For remediation, one of the best strategies is called adversarial training. The best way to think about this is like giving your AI a vaccine. You deliberately show it these tricky adversarial examples during its training. It learns to recognize the invisible noise and correctly classify the image anyway. It learns to see the panda. no matter what. And on the prevention side, it's all about being proactive. This isn't a one-and-done setup. It means you're constantly testing your models against the latest attacks. You're using specialized security management tools, and you're plugged into the research community so you know what new threats are coming down the pike. And look, if there is one thing you take away from all this, let it be this. AI security can't be an afterthought. You can't just build a model and then try to bolt on some security at the end. Making it robust against these attacks has to be a core requirement, baked in from the very beginning of the development process. The source material really wraps up the whole philosophy perfectly. It says, the future isn't about building a perfect, unbreakable defense, because that's probably impossible. The real goal is resilience. It's about building systems that are smart enough to detect, respond to, and recover from attacks when they happen. And that leaves us with this final thought. We're building these incredibly intelligent systems, right? They're smart, but as we've just seen, the real challenge isn't just about making AI smart. It's about making it wise. Wise enough to see the invisible,